So mesoscale models play an important role in modeling the atmospheric flow. They are very good at simulating the small-scale weather patterns like sea breezes and katabatic winds at the scales of a couple of kilometers or more. But then we also have these microscale models like WindSim that have a high-resolution topography and roughness data, but they lack much of the or some features of the physics that are included in those mesoscale models. So we would like to create like a best of the both worlds model that combines the transient atmospheric flow modeling capability of the mesoscale model to the high resolution topography in the microscale model. And so traditionally at WindSim, we have actually, what we have mostly been interested in are the so-called speed up factors inside the domain. So when you run a WindSim simulation, it has, you can select the inflow wind speeds at the inlets, but they follow so-called Reynolds number similarity, by which the inflow speeds don't actually matter that much for the results of the simulation. What the simulations are used for are to calculate the relative changes in wind speed and direction with respect to the met masts. So the absolute values of wind speeds that you get from the Phoenix solver, they don't really matter. It's the relative changes inside the domain that we mostly care about. But here we have decided to try to extend our services more towards the screening market, which is pre-construction of the measurement campaign. So you want to screen different sites, and then you need to use the absolute wind speed information from the mesoscale model to and downscale it using the WindSim CFD simulations to get some early identification of where the high wind spots are located and what the wind speeds are going to be like, and also get good information at high resolution to talk to the landowners. So there are a couple of different meso-microscale downscaling approaches in the literature, which have been, so this is a topic that has been studied for a long time. And the simplest, or not simplest, but the approach that comes to mind first, if you've got used to running the WRF model, is this physical mesoscale downscaling, where you use the boundary conditions from the WRF model as an input to the CFD model, and then you can run it over time in transient mode to get a downscaled version of the mesoscale field. But the other approach is the so-called point-like mesoscale data assimilation, where you just take the mesoscale data and you input it to the standalone WindSim simulation as like a virtual metmast. So we are going to use both this boundary condition approach and this point-like mesoscale assimilation in combination to create this new downscaling solution. But first, I'm going to tell you what's wrong with using the mesoscale data directly as virtual metmasts in the WindSim simulation. So first of all, as input data, we use the new European Wind Atlas, which has great average wind speeds. It has coverage for the entire Europe. At a resolution of about 3 kilometers, and the data that's available online spans about 14 years and vertical levels from 50 to 500 meters. And the idea here is to simply see what happens when you take the data. You run the standalone WindSim simulations. And you will use it as a virtual metmast inside the wind resources module. So here I have a video for the Hundamer case that you've seen many times in these today before already. So it's surrounded by 2 sites or almost 3 sites by water. So it's a relatively should be a relatively simple site to combine the meso and microscale simulations using a virtual metmast technique. But here I take 4 mesoscale points marked by these gray dots here. The spacing is 3 kilometers. And this is the output from the wind resources module, which shows you the mean wind speeds. And if you pay attention to the mean wind speed values, when I loop over the different mesoscale data points. So when I click here on the climatology, it changes the only calculates the wind resources based on one mesoscale data point, one of these 4 points. So here you have a maximum wind speed of 11.6 for this point, but then you can have significant differences in the maximum wind speed. It changes from 11.6 to 10.4 meters per second at the highest measured wind speed. So it's very difficult because of the changes in mostly in the terrain and roughness and the physics between the 2 models to get consistent results between the different virtual metmasts using this technique. So we want to design a method that decreases the uncertainty or the variability in the wind resources assessment between the different mesoscale data points that are located inside the WindSim domain. So the design criteria, we had a couple of them. So the method is supposed to use almost all the mesoscale points inside the WindSim domain. And because we are in the business of making money, we want the method that's easy to communicate to people who are already familiar with WASP. And it also has to be robust, so no fitting parameters like machine learning. So there are a couple of steps we do here. So first, we look at the mesoscale time series of the mesoscale runs. We have used so New European Wind Atlas, yeah, it's 3 kilometers and every half an hour. So every half an hour, you have a mesoscale output field, and then you look at the direction of the wind inside the mesoscale domain. And then you take the directional averages of the wind fields based on where the wind is coming from inside the mesoscale domain. So then you get these time and sector average values of mesoscale fields. And what we can do them is we can use them as boundary conditions to WindSim. So here's an example of New European Wind Atlas. So we have used 12 sectors, and this is sector direction 150 at the horizontal wind speed at 83 meters, which is the measurement height at Hundamer. And here we have specified this as boundary conditions to the WindSim simulation. And when you compare these 2 fields, you can see that they have a lot of similarities. So you have low wind speeds in the northeastern corner, high wind speeds in the southeastern corner, and so on. But what you don't see, obviously, in the mesoscale simulations is the high wind speeds at the Hundamer mountain. And we've also used a nudging technique to help correct for the difference in physics between the two models. So we use modest nudging to force the wind field to be closer to the sector averaged mesoscale field. And then comes the WASP terminology. So in the same way as you would produce a wind atlas using WASP, you first have to perform the so-called generalization of the mesoscale data. And how we do it is oops. What am I? Go. Yeah, it starts from the beginning again. No, not slightly. Yeah. Yeah. Okay, so we have the mesoscale points located every 3 kilometers inside the domain. And what we want to use is we want to generalize it. We want to represent each mesoscale wind vector. And this is a time-dependent vector. So every half an hour at each mesoscale point, we get a new wind vector. And we want to represent that using the sector average mesoscale values as basis. So we want to use these as basis functions. For every mesoscale wind vector at the given instant in time, you can define the sector that lies to the left of the wind and the sector that lies to the right of the wind. And then you can represent the mesoscale field as a vector combination of these two sectors. So you have an equation where you have these two multipliers for the left and for the right, and these are unitless. So the left and right-hand sectors, they have units of meters per second. So these two coefficients for the left and right-hand sectors, they are unitless. And then, for example, for 1 year, for each mesoscale point, we keep track of what the left and right-hand sectors are, what the indices are, and what the values for the different coefficients are. So we get this matrix table for each mesoscale point as a function of time. And then comes the application step, where we, instead of using the mesoscale average fields, we use the corresponding microscale fields from the simulations where the mesoscale boundary conditions have been used. And we scale them using the same factors. So now we don't know yet what the microscale wind is going to be. We know what the wind speeds are on the right-hand side and the left-hand side sectors, and we know the multipliers. So it's just a vector sum to calculate now at every instant in time at the mesoscale point what the microscale wind is going to be. And then you can, let's take a recap of this, because I think many people are going to have trouble following this. So what we basically do is we take the mesoscale wind and then we scale it using the speed up factors and directional shifts going from the mesoscale to the microscale domain. That's all what we do. So we know comparing the mesoscale field and the microscale field, you know what the speed up factors and the directional shifts are, and you use them to scale the mesoscale field to get the microscale wind. That's all that this basically does. And we can then, because you have the time series of the microscale wind, you can then use them directly as an input and just run, print them in a TWS file and import them in the objects module. So now with the new downscaling, when you look at the maximum or the minimum wind speeds, you will see that they are much more in line. I'm now looping over the different virtual met masts. Let's take the animation again. So if you look at the minimum wind speed or the maximum wind speed, they vary by about 1% between these data points. So now we have greatly improved the consistency in the wind resources downscaling from mesoscale to microscale using this procedure. And what we can also do is we can compare the maximum power density figures, which also gives you a sense of how well this method is able to capture the variability in the mesoscale field. So not just the mean values. And for the naive virtual metmast, we get more than a 12% error, the uncertainty. So this is what we do. What I do here is I loop over the mesoscale data points. There are 25 inside this domain. And then I calculate what the maximum power density anywhere inside the domain is, the average value and its standard deviation. And for the naive virtual metmast technique, it's almost 12%, the standard deviation, but it's greatly reduced to less than 3%, almost 2%, if you use this WASP-like new downscaling technique. So we have introduced this new WASP-like downscaling technique, and this is not yet available in WinSim, unfortunately. We might include it in the future versions or the accelerator, but now if you want to do screening using this technique, you can reach out to us and we will do it for you as a consulting project. And the goal is to reduce the micro downscaling uncertainty in the Wind Atlas procedure. And the validation is ongoing, but the validation, it's a bit difficult thing to do because still the majority of the uncertainty in the absolute wind speeds, in the mean wind speeds, comes from the mesoscale model. But still, it's really important to not introduce any additional uncertainties here at the microscale modeling level, and we believe that this technique has potential to be used there. So if you're interested and you want to do screening, reach out to us and we will do consulting for you. Thank you.
Oh, hold on. We're not finished yet. We have questions.
Okay.
So I want to say, if there are any more questions, just chat them in, put them into the chat. So far we have 3, you all.
Okay.
The first one, I think that you addressed sort of already, at least partially. So maybe you can address it in more. So the question is the meso-micro scale coupling currently discussed already available in the WinSim accelerator? What's the plan?
The plan is to include the screening tool to be to work in conjunction with the map module that Teo presented. So it's supposed to work as easily as drawing a rectangle that Teo showed you on the map. Then we would automatically generate the model and the roughness and elevation fields and couple the microscale model using this technique to the new European Wind Atlas or other datasets, other mesoscale datasets that we might have then. So it's not, unfortunately, it's not yet on the accelerator, but it's in the roadmap to include it. Yeah.
Great. Next question: which database can we use to import into WinSim to do mesoscale?
So as it currently stands in WinSim 12, there it supports the default outputs from it supports most WRF output fields, the netCDF files. We have the mesomicroscale coupling console inside WinSim 12 that you can convert these netCDF files to these sector average fields that you can then use to run the mesomicroscale coupling. Yeah, so we can use you can use most of your own WRF simulations, and you can also use the new European Wind Atlas, which is also supported by the WinSim 12 right now. Yeah.
Okay. Great. Next question: is it easy to reach conversions with MMC? After SOM, I launched MMC, and the residuals for K and EP were hard to converge in 5 cases out of 6 cases from SOM. I was wondering if there was some problem in the downscaling of turbulence.
Yeah, so we don't use the turbulence fields from the WRF data or the mesoscale data because they are the parameterization of turbulence in the mesoscale model is quite different. So there, we have had good experiences reaching convergence, but specifying the turbulence boundary conditions with the mesomicroscale coupling is quite difficult. So yes, we have seen individual cases, yeah, where the turbulence convergence has been somewhat non-trivial. Yeah, but we are working on that. Yeah.
Okay, good. We got another one from Ilir. Hi, Ilir at Brightwind. Is it possible? You touched on this a little bit. Is it possible to obtain good results with MMC using freely available mesomicro data such as New European Wind Atlas?
Yes. So the WinSim 12 right now it supports the New European Wind Atlas. So what you can do is you can go to the website and you can download. You can draw a rectangle on the map that's slightly larger than the computational domain, and you can use that in the WinSim mesomicroscale coupling procedure to calculate these fields. Good results. So because this is mesomicroscale coupling, the quality of the mesoscale model does have an impact, obviously, on the quality of the results. We have mostly used, actually, most of our experiences are using WRF data from an external vendor, and we have got some good results using that. We don't have yet the extensive experience with the New European Wind Atlas data to say how good the downscaling results are going to be, but this is a new tool that we have just introduced. It was one of the last additions to WinSim 12 to support this WinSim, the New European Wind Atlas. So we are still trying to gather that experience, how well it works ourselves. Yeah.
Yep. Good questions, good input. I think that was the last one. So thank you to everybody who came with questions. Now it's back to Vincent. Just give us a small moment, and then Vincent will be back on. Just a second.
Sonja. Okay, so I'm back, and now I'm going to do a quick presentation about my master thesis, where I did CFD simulations of local wind fields, where I studied the parameters. So here. Yeah, so the goal and the objectives of my master thesis. I can start by telling that I went to, I did my master thesis at NMBU outside Oslo. And here I had, I met Arne. He was lecturing in wind. And then we were introduced to the WindSim software. And I was very interested at once. I thought it looked very good and very interesting. So when I was going to do my master thesis, I decided to go for WindSim. And because I also liked Arne as a person. He was very smart and a funny guy. So I'm glad I chose to write the thesis for WindSim. Yeah, so back to the goals and the objectives. I was going to check for the parameter sensitivity and also grid dependency, and we also took the simulation time into consideration. So the site selection, I had a number of sites in Norway where we had some reference met masts, and we ended up picking a site outside Sandnes, which is in the southwest of Norway. It was a site with high or relatively, it was semi-complex terrain with elevations between 100 and up to 400 or 500 meters. So the first step was to get the terrain data. So I downloaded 2 DTMs from høydedata.no, which is, I think it's a governmental where you can get from Norway, where you get high quality elevation data. So I downloaded one set with 10 meter resolution and another one with 25 meter resolution, both in the same extension of 31 kilometers. The reference data was from a Corinne Land Cover 25, the 2018 version. And I used Global Mapper to do the layers and to export it directly to the WindSim format, GWS. So the method, the first was to define a base case. So that is what I have called S1. So that's the 25 resolution model with the 10 kilometer buffer and about 3.5 million cells. And then I created different cases. So I had 4 different parameters. So that was resolution. So I had a range of different resolutions from 10 meters to 500 meters. Next was the domain buffer size. So that's from the refinement area and out to the border of the domain. And that ranged from 1 kilometer and up to 30 kilometers. The next was the refinement area. So here I had no zero refinement buffer. So that means the refinement area was only covering the area where the turbines were placed. And then it increased up to a maximum of 7 kilometer of refinement buffer. So that's quite a large refinement area. And you can see it's 20 million cells. And it was, I can say as much as in terms of simulation time, it took about 3 to 4 days on my laptop to run this one case. So I would say, I said to Arne when I joined WindSim and I've been working, so last year, that it would be great for me if the accelerator was launched when I did my master thesis, because then I wouldn't spend weeks running the simulations and burning out my private laptop. The last parameter was the vertical resolution. So then in the base case, it was 25 layers, like the default value in WindSim 12. And it ranged from 10 to 50 cells in the vertical. And all the vertical distributions were geometrical. So I ran because of course, as I had my own private laptop, I had to limit the simulations to a single sector, or I would spend years running the simulations. So I went for a single sector simulations. I simulated the 330 degrees sector. I had convergence criteria of 0.30 and 5, so quite tight. And yeah, it took about 800. I ran about 800 iterations for every sector or every case. So of course, with low resolution, it converged way earlier, but in some cases, I had to run the extent of 800 iterations. So in WinSim, I got assistance by first the PhD student at the time, Pablo Duran. So he was working part-time in WinSim, and he also did his PhD in WinSim. So he was helping me to set up the models. Yeah, so I positioned the turbines in a large triangle in the middle of the site. And this was, of course, to capture the terrain effects in different positions and compare the effects by changing the parameters for all the positions of turbines. And also I positioned turbines at the MatMast positions to capture effects there as well. Yeah. So for the data processing, I ran the terrain, established my terrain model, I ran the wind fields, and then I placed the objects. The next step was to export the vertical profiles for every turbine position at the site, and then I had to do interpolation to get the simulated wind speed at the different heights. So we specified 3 different heights, 19 meters above ground, 49, and 100 meters above ground, to compare the effects as we at higher heights. Next thing was to normalize the wind speeds to the reference point of MatMast position number 3, so that for all the turbine positions, the value is 1 for the MatMast 3 as a reference point for the speed ups. So in the results, I looked at the variations in the speed up, relative speed up for all the turbine position in relative to the position of MatMast number 3, which was all southwest in the area. And I reported the results by using bar charts where I had the different parameter settings in different colors, and I had 1 bar for every turbine position. So as you can see from the top here, maybe I need to activate this laser pen. Is it this one? Yeah, laser pointer. See if I can get it here. So here we can see it's normalized on the position of MatMast 3, which was located here at the southwest point of the wind farm. And then it's the relative speed up for all the turbines positions in the whole area. And we can see some turbine position, there is large variations between the different resolutions. And especially in the positions where the turbine is placed in a valley or behind a hill or on top of a hill. So on the top of the hills, we can see the higher resolution models. They predict higher speed ups on top of the hills and ridges. And behind the hills and ridges, we can see the speed up, the predicted speed up is way lower. So this indicates that there is a clear trend that the higher resolution captures the areas of low wind speed and also the areas of high wind speed. Maybe I need to deactivate the laser pen to continue. Oh, okay, there we go. Yeah, so for resolution, here we are looking at the maximum and minimum resolution. So this is 10-meter resolution to the left and 500 to the right. So of course, this is a very coarse model. But you can see that when we run a coarse model, we have, in general, we have higher wind speeds in the whole domain. While with the high resolution, we capture the areas of low wind speeds and potential recirculations. And the bottom figure here, ABC, so this is actually, the A is 50-meter resolution, so it's not that coarse. The B is 25, and then you can see the change from 25 to 10-meter resolution. So this is at 19 meters height, so it's fairly close to the ground, but you can see that there is a huge difference between 50 to 10 meter resolution in terms of capturing the areas of low wind speed. And you can also see the vectors here, they are pointing in all directions, so there's clear signs of recirculation. And yeah, this trend, it continues. So I did not include, unfortunately, the figure for 49 meters above the ground, but in that case, it's almost absent in the 50 meters, but it's still a lot of low wind speed and recirculation going on in the 10 meter resolution model behind this hill. So yeah, to do this, I used the results module in WindSim, and then I filtered the vectors on the wind speed. So then I captured all the vectors, filter out only the ones with I think it was below 2 meters per second or something. So that's how I created this graphic. And yeah, so I will come back to in the conclusion, but resolution is a very sensitive parameter. And high resolution, the trend is that you will capture the high wind speed zones and also the areas of low wind speed and recirculation. The next one is the domain buffer size. So this is, of course, an important factor when you do the domain buffer size is where you place the border on your site. So this will, of course, vary if from site to site. Yeah, where you would like to position the border. So, but in this case, I had the 10 kilometer buffer. So then you can see at my close to the border up here, I have this ridge, and you can see that the inlet direction was 330 degrees. So the arrow shows the inlet direction, and you can see we get a significant speed up very close to the border here at the inlet. It's about, yeah, I was between 12 and 14 meters per second with the speed up in this. Yeah, I need to activate the laser pen because I'm pointing a lot here. That was not the right one. See here. Yeah, so this was where I was pointing now. So you can see this hill. And then when we increase the buffer size to, I think this might be 20. This was 5, I think, and this is 10 kilometer buffer. And you can still see the speed up here on the ridge and mountainous area here close to the border. And then when we increase the border to 20 kilometer, we can see that the speed over this hill, which is like close and perpendicular to the inlet wind direction, close to the wind farm. Now the wind speed over this ridge is below 9 meters per second. So there's a significant difference between having 5-10 kilometer buffer going up to 20 in this case with the current inlet direction. And this, of course, affects the wind speeds at certain points in the wind farm. And as you can see, in general, for all the positions, the trend shows that there is not very big differences when we move from 20 to 30 kilometer buffer. So I argued that there was some sort of a grid independency when we reached about 20 kilometer buffer zone. So the domain buffer size in my case was sensitive. The next parameter was the refinement area. So this was a bit more tricky to investigate to find a clear trend. There was variations in the reports and the bar charts, but there was no clear trend in the charts. But I did some investigation in the wind direction, and I could see that when I have a small refinement area, I always forget to activate this laser, sorry. Yeah, so here we have the inlet direction, and in this case we have a pretty small refinement buffer of about 1 kilometer. And here I have dived into the results, and I have checked the wind speed over the ridge and also in the valley down here close to the wind turbines. So I can see here when I run with the 1 kilometer refinement area buffer, I have a 2.5 meters per second simulated wind speed here down in the valley and 9.3 over the ridge at the inlet wind direction, while in the extending the refinement area up to the ridge, I can see it's over 1 meter per second lower over the ridge, even at this point where it's a bit higher than the surrounding area. And I can also see that I have a lower wind speed than in the valley. So there's about more than 1 meters per second change in wind speed when I extend the refinement area up to the ridge here. Of course, this is specific for this site, and it will also depend on the topography of the specific site you are running simulations on. But it shows that there is you need to take into consideration where you place the refinement border, and having a sufficient refinement border might be of interest. So the next one is the vertical layers. So I ran with 10, 25, 35, and 50 layers in the vertical. And from the verticals, I could see that the 10 cells in the vertical was too little. So I had about I think 5 cells in below 100 meters, which is too few and not to be recommended. While from the base case with 25 cells in the vertical and up to 50, there was about 11 cells in the first 100 meters in the base case of 25 cells total, and up to 18 cells below 100 meters in the with one model with 50 layers in the vertical. So I would say that the recommendation would be to have at least 25 cells in the vertical, and also the geometrical expansion works well. Then you get a high amount of cells in the turbine operating area with the expansion towards the top order. Yeah. So to conclude, my results show that the resolution is a sensitive parameter where if you want to capture the high wind speed zones with the areas of high speed ups, and also the locations with low wind speed and potential recirculations, you would like to have, I would say, at least 25 and probably 10 meters resolution in terrain that is semi-complex and more complex. Also, the domain size is a sensitive parameter, and it's important to have a sufficiently large domain buffers, so you allow the flow to develop before entering the wind farm area. In terms of refinement area, there was no clear trends, so it will be site dependent. It depends on the topography close to the wind farm, and so you might consider extending the refinement area if you have some complex terrain close to the wind farm. The vertical cells, it's clear that our default settings in WinSim 12 with the geometrical distribution and 25 cells should be a good starting point when establishing the numerical grid. And you might consider increasing it depending on the site. And if you have turbines that are extending higher, the operating area of the turbine increases up to 300 meters, then you might consider increasing the amount of cells to get enough cells in the turbine operating area. Yeah, so thank you a lot for listening, and see you again after the break. I guess Lil maybe would like to say some words.
Thank you, Vincent. Great. So we've been running for almost 3 hours, so we will indeed have a break, but please do continue to ask questions in the chat. We love that, they're coming in. So just a small reminder here now. After the break, we are going to do the last part of the meeting, focusing on user presentations. So we have 4 lined up, starting with Ryan from Ventient, then with Nikos from RWE. I'm going to step in for Rich from Pattern, and then Giorgio from NL, and we'll cover various quite interesting use cases, I think, so that might be interesting for you to follow. So we will start again at 1 o'clock, so a little bit more than an hour break now. So we'll see you on the other side.